Equilibrium, this could be its own unit, but it's a relatively minor topic. And so I just tack it on here to the end of solutions and just put the two of them together. So we need to discuss the idea of dynamic equilibrium first. When we talked about reactions early on, we would always draw them with a single arrow going this way. And when we draw them that way, we're implying that the reaction only goes this way and that it goes completely this way. Well, the reality is it's not that simple. Most reactions are reversible, meaning they can go forward and they can go backwards. And they tend to do it at the same time. Some reactions are not reversible. You can't make fire go back into a match and get the wood back. It's not reversible. That match is gone. But a lot of chemical reactions are reversible, and we have to take that into account. So when we get these rates to be the same, we say that the reaction is in equilibrium. That how fast it's going this way and how fast it's going this way are the same, then we would say they are equal or in equilibrium. The key thing there that this equilibrium is dynamic, meaning the reactions are still going on, but the concentrations stay the same, that there's still some of this reaction going this way, there's still some of this reaction going this way, but the amount of each of these remains the same. The amount of these remains in equilibrium. Once again, the easiest way to think about dynamic equilibrium is think of a sports game. You know, you're watching a basketball game. There's 10 players on the court. Always. If a new player comes onto the court, an old one goes off. So the players may change. It's dynamic. They're changing. But the total number of players on the court remains the same at 10. And so that's an equilibrium. And so we could say that you watching a basketball game and you got players subbing in and out. It's a dynamic equilibrium. It's moving, it's changing, it's dynamic, but everything remains the same. Okay. We can also have what we call a physical equilibrium, which between two phases of the same substance. Go back to that water bottle that we had talked about a little bit ago when we talked about vapor pressure. You know, you leave your water bottle sitting on your table after you've drank about half of it. You're going to see some droplets on the top and you're going to see some condensation. This is dynamic. You're always getting more water evaporating and you're getting more of the water vapor condensing, coming back down, and then it's just going to keep changing. The water molecules that are vapor this morning may be in the liquid in the afternoon. And they may be back in the vapor again this evening. Or they could stay in the liquid for 5 days. You know, but it's going to be moving and changing. It's dynamic. So in terms of reactions, we use what we call as Le Chatelier's principle. So Le Chatelier's principle states that a system in equilibrium will respond in order to restore equilibrium. This makes sense, especially if you think of it in terms of biological systems. You change something, that system is going to respond in order to try to make everything equal again. Nature likes balance. Nature likes things to balance each other out. All right, so you could do one of the following things to a system to change it. You could add or remove some of the chemicals, whether from the product side or the reactant side. You can change the temperature, or you can change the pressure. All right, so let's look at an example reaction to see how this works. So the way I like to think about this is that what's going on is you want to look at how we need to make things equal again. So you can think of it as kind of like things moving up and down, and then how do we need to move things to make them go back to being in balance. So, for example, if I remove some of the ammonia, the NH3, if I remove this side, then all of a sudden this side drops down. So this side is lower because I removed some of it, and this side's still relatively high. Well, how can I make them balanced again? Well, if I take some of this and move it to this side will go down, and this side will come up, and then they'll be equal again. So it's going to move the reaction to the right, that it's going to want to go forward. All right, so that we would say it shifts that way. Okay, decreasing temperature. Temperature has its effect when we have a reaction that involves heat. So I've got my delta H, that this is an endothermic reaction. Heat is being added to the reaction. And so the easiest way to think about this is to kind of think about where it belongs in the reaction. This is endothermic, so it belongs on this side. So I could write this as N2 plus 3H2 plus 184 kilojoules equals or yields 2 ammonia. Okay? So I could write it over here. So if I decrease the temperature, if I'm over here on this is the temperature, the heat side, and I decrease this side, and this side stays high, what's going to happen? Oh, I can take some of this and I can go over here and it'll give off some heat because I'm going in reverse direction. And then this side will go down and this side will come up. So it'll cause the reaction to shift to the left and to go in reverse. Okay, pressure. Pressure only comes into play when you're dealing with gases. And when you increase pressure, the reaction is going to shift to the side with the fewest moles of gases, meaning it's going to move to the side with less gas. That's essentially what's going on. So if I increase the pressure, it's going to want to have less gas. If I decrease the pressure, it's going to be willing to have more gas. So by increasing the pressure, I've got 4 moles of gas on this side, 1 mole of nitrogen, 3 moles of hydrogen, and I've got 2 moles on this side. So by increasing the pressure, it's going to drive the reaction to the side with fewer, which is this side over here with 2, causing the reaction to shift to the right. That's the basis of Le Chatelier's principle. Whatever side you add or subtract things to, the reaction is going to shift either to the left or to the right to try to balance it back out again. All right, now in a slightly more technical sense, we need to talk about how we deal with concentrations at equilibrium. So we can express the equilibrium of a reaction by its equilibrium constant. Every reaction is going to have a KEQ. And so KEQ is a mathematical expression of what's going on with that reaction. So if you have a reaction of, we call it kind of the standard form. So A plus B gives me C plus D, where the lower script numbers are the coefficients. That you're going to take the concentration of your products over the concentration of your reactants. And each one's going to be raised to the power of its coefficient. So if these were all 1s, then I'd have a bunch of 1s here. But if this had a 2 in front of it, there'd be a 2 here. And I would square this. You'll kind of see it as we go along. So that's KEQ. So KEQ is always concentration of products over concentration of reactants. Where we had like delta H was final minus initial, you can think of KEQ as final over initial. That it's what we end up with over what we start with. This equilibrium constant will always be a ratio of products over reactants. And we use their coefficients. And there are other forms that we can use depending upon what you're talking about. When we get into acids and bases, you can have Ka for acids, you can have Kb for bases. You can have solubility where you have what's called KSP, which is the solubility product. It's all related and they all work exactly the same. So we're not going to go into all those weird ones. All right, let's talk about how do we actually use this thing. So KEQ, when you look at a value for KEQ, it tells you what the reaction's doing. So for example, if K is a lot bigger than 1, that means that reaction is going to favor going to the products. Because remember, when you have a fraction that's a lot bigger than 1, that means the numerator is huge relative to the denominator. Like 5,000 over 5 would give you 1,000. So the numerator is large. And since products are the numerator, they're favored. If KEQ is much less than 1, it means the reactants are favored, that the reverse reaction is favored. Because that means the denominator is big. So let's look at an example and see how this works. So here's a reaction between nitrogen and oxygen. And we want to find the value for KEQ if these are the equilibrium concentrations. So I give you the concentration of the nitrogen, the oxygen, and the nitrogen monoxide. And so you need to figure out what KEQ is. And so we're giving you these. And so is the products, NO. So we take NO squared because of the 2 in front. So we take the concentration of NO goes here, and then the reactants go on the bottom. And both of them have a 1 in front, so they don't have any exponents. So it's just simply the nitrogen times the oxygen. Put that all in. Usually these don't always cancel out, but we're going to not worry about units on KEQ. So you get 1 times 10 to the negative 5. That is a small KEQ, which means the denominator is bigger, which means nitrogen and oxygen are favored. Okay, and this makes sense. We don't have a whole bunch of this flying around in the atmosphere. It's mostly this. And so that's what's going on there. And so KEQ is one of those things that I want you to be exposed to. I'm not going to do a whole lot with it in this course. It's definitely more of an AP or a college chem level type thing. But that's an introduction to KEQ for you. So you just figure out your expression in terms of concentrations, plug in your values, and you can get an answer.